Hey all, so we're going to keep going with semester 2 things. One thing I want to give you a reminder of, especially as we continue on and we're starting to look towards the AP test in the spring, your semester 1 materials are always going to be available as in the form of the guided notes in the course materials, which is at the bottom of the new semester 2 Google Classroom. So if you want to go back, look through the guided notes, the PDFs, those are down there as a nice study tool as we get farther along. Now, we're going to keep talking about growth models. Last week you did the exponential growth model and looked at that. This week we're going to talk about the logistic growth model, which is much more complicated, which thankfully means it doesn't show up quite as much on the test and things like that, but it does show up a ton in science classes and things like that, because the logistic growth model is the model that a lot of populations actually have versus exponential. So we have our logistic growth model here. Here's what it looks like in terms of the differential, which is dp dt, the change in population over time, is equal to constant p, so it looks similar to the exponential growth model, but with additional parentheses right here where it's 1 minus p over big K. And the big K is the carrying capacity. So in terms of what it would look like, if the population starts below the carrying capacity, which is how much that the actual environment can sustain, it'll go up and then it'll even out like this. If it starts above, it'll look more like a exponential decay model like so. But mostly we're worried about here, where this is your carrying capacity. This is how much life the environment can actually sustain of an organism or of a species. So now one thing that we do if we were in class and we had our 50 minutes together is I'd walk through how you can go from this differential equation to the actual model here. But instead I've given the algebraic description here, and I just want to go over it because it does address a couple of important strategies, even if we're not going to do the entire proof. So just as before, we're going to separate the variables. So everything in terms of p comes over here, and k dt is left over on the right side. One thing that I will show that I think is important is this idea of when we divide p over here, then distributed, and then here multiply each side by k to get rid of the fraction in the denominator, so that the thing we're actually integrating at this step is k over p times k minus p. Then for this section here, the strategy that we're using is partial fractions. Sorry if you can hear my dog in the background. She's being a little dingus. We're going to use partial fractions here, where we have a over p plus b over k minus p is equal to k over p times k minus p. And we have our p terms and our constant, which means here ak equals k, a equals 1. Plug that into the p terms, b equals 1. If you want to expand that out and practice your partial fractions, feel free. Then we can separate those into two fractions and take our, add those in, take our antiderivatives. So we have log p minus log k minus p equals kt plus c. Put the logs in one form. Since these are subtracted, this is divided. Raise to the power of e on both sides. We again get c. This becomes a plus. This becomes, just like we looked at with exponential, e to the kt plus c, which is e to the kt times e to the c, which is its own separate constant. Like we see here, we can plug that in and realize that our c is equal to p naught over carrying capacity minus p0. More solving for p by itself, and we end up with our final function here, like so. you're not going to have to use all of this all that much. The type of questions that's most likely to come up here is when you're given this model, you are going to be asked about K, little k, or big K. And one thing that's really important here is the limit as t approaches infinity. If you look at this graph that I've made of P of t, that's equal to K. So sometimes that's another type of question that you might get asked. So let's actually look at using these complex functions. So in number 2, I just copy and pasted the functions here for us. A growth of a community with an initial population of 100 individuals is modeled by dp dt equals 0.08p times 1 minus p over 1,000. Find the population in 10 years. Now, one thing that you can do is do the separation of variables, use partial fractions, and solve, which is what some calculus teachers will ask you to do. And if you don't have this memorized, that's a very understandable thing to do. But what you can do is that what I will recommend that you do is say, oh, that's the logistic growth model. Little k then is 0.08. The carrying capacity is 1,000, since that's right here. Little k is right there. So I can just plug them in to my final question, and it's asking after 10 years, so it's asking P of 10. Well, plugging in the numbers that are given, we end up with 1,000 minus 100, since this is our P sub 0, over 100. And then e to the negative k, so 0.08, t is 10, plus 1. And the numerator should just be the carrying capacity of 1,000. Now from there, we can do some substitution, some simplification. If we don't have a calculator, you'll end up with 1,000 minus 100 over 100, which is 9, e to the negative 0.8 plus 1. And this is about as far as you would be expected to get without a calculator. What that tells us with a calculator is that that is equal to 198 individuals after 10 years. And again, very nice, straightforward problem if you can identify that's the logistic equation and can come up with this. It's unlikely, but that is something to think about. Now, here's one of those cases where this is not given as a growth model, but it is given in a much more complex problem as a separation of variables problem that you actually can use the logistic equation for. This is sort of the highest level of difficulty of separable equations, because you'd have to use partial fractions, you'd have to use a lot of very complex numbers. But if you can recognize that this sort of looks like the logistic growth model, it makes it a much easier problem to look at. So the first way I can tell that this is a logistic growth model is that I have y on the outside here, and then we have fraction, and then a subtraction problem. So this is sort of the key in, okay, we have an equation that would require separation of variables. We have our parenthetical. Okay, the other thing is this idea, because if you remember, the limit as x in this case, because the variables changed up, approaches infinity, of the population model is just big K. So often if you see a separation of variables equation and a limit as it approaches infinity, ask yourself if it's a logistic equation, which in this case it is. So we want to manipulate it into this model, and then our final answer is just big K down there. So the first thing that I'm going to do is I'm going to consider 0.0045y times 1 minus 2y. And the first thing that I need I need a 1 here. Right now I have 100. So just like I would do for many of these, I would multiply by 100 over 100 and distribute. So then what I end up with when I distribute is I end up with 0.0045y times 1 minus 2y over 100 times 100, because I'm distributing just the denominator for now, because that's what turns this 100 into a 1, which is what I want. So then with a little bit more simplifying, I'm just going to take the coefficients, multiply those together, simplify this, and then I end up with 0.45y times 1 minus y over 50 is the same as the expression we started with. Oh, well, now we're in logistic form. So this is our k value. So therefore the limit as x approaches infinity of f of x is equal to 50. You can use separable equations, you can use all these things, but it makes it a much more straightforward problem. So give it yourself some time, work with the logistic growth model. Let me know if you have any questions, and if you are still struggling with anything from the changeover for semester 1 to semester 2. Talk to you later.